trig ratios, only now using the unit circle, or kind of applying stuff that we did with right triangles, now applying it to a circle. So we're going to focus here on the picture first. So here, it's got a lot going on. But what I want to point out first is what we're talking about now is if we have a circle on the coordinate plane, so we have an x and a y, I'm going to put a point on that circle. So that's what this xy is showing. So then what people started to notice is that if you put a point anywhere along the circle, where the circle's the middle is the center of the coordinate plane, there's this nice little angle here, and then what they notice is that we have this radius of our circle that goes out to that particular point, and then if you really look at it, notice there's some dashed lines here. We can actually make a right triangle out of the radius of the circle, this angle, and then the x and y values from that circle. And there's two ways to do it. I'm going to focus on this upside down one to do it. So with that right triangle, we have our three sides. We have this one that's along the x. We have this one that's here, and that's actually this y distance. So I'll put the y over here. And then we have our third side of our triangle is that hypotenuse, or the r. So then what they notice is that instead of having to necessarily have a specific right triangle, what we can do is still use our SOHCAHTOA, but start with a point on a circle rather than having a triangle. So then what they notice is from this, the x value is like the adjacent side, because again our angle's coming out of the middle. It's like the adjacent side of that little right triangle that we can draw in there. The y value is like the opposite side of the little right triangle that can be drawn in there. And then this radius of our circle is like the hypotenuse of that little right triangle you can draw in there. So then what they can do is if I give you this point, I give you the x and y, we can use kind of this idea that we're trying to make a little right triangle in it. And we can find the radius of the circle even if we're not giving it, because we can use this reimagined version of the Pythagorean theorem. Because x is like the adjacent side of a right triangle, y is like the opposite side of the right triangle, and r is the hypotenuse of that triangle. So again, still trying to think of it as SOHCAHTOA, only instead of using specifically a right triangle, where we have an opposite hypotenuse and adjacent side, we can just be given an x value and a y value on a circle, and then imagine drawing in a right triangle. So we can apply everything we do with right triangles now to this point on the circle. So you're going to be given an x and y value, and then we can use this reimagined version of the Pythagorean theorem, where x squared plus y squared equals r squared, to get the hypotenuse, because the hypotenuse is the radius squared. So usually it was a squared plus b squared equals c squared, where c had to be the hypotenuse. Now we're saying the radius of this circle would be your hypotenuse, so it's our r squared here. So then we can use those three values, x, y, and r, to write the trig ratios like we did before. So, and I don't know if you can see it, but you can kind of see on my poster the big letters of x, y, and r, and it all stems from being able to draw in that right triangle from that circle, and then applying it, the x values as the adjacent side of that right triangle, the y value is the opposite side of that right triangle, and the hypotenuse is the radius. So then we can write out our ratios now using x, y, and r instead of opposite, adjacent, and hypotenuse. So sine was typically opposite over hypotenuse. Well, opposite is now the y value, hypotenuse is the r value, so sine is y over r, or the y value over the radius. Cosine was typically adjacent over hypotenuse, so it was the adjacent is the x value, the hypotenuse is the radius, so it's the x value over the radius, so x over r. Tangent was typically opposite over adjacent. Opposite is the y value. Adjacent is the x value. So tangent is y over x. So that's where they all stem from. And then these three are still the reciprocals of it. So sine reciprocal is still the cosecant. So it's radius over the y value. Secant's reciprocal is still secant. So it's radius over the x value. Cotangent's reciprocal is still cotangent is still the reciprocal of tangent, so it's x value over y value. So then what we can do is now we can use these ratios with more values. Because we were just talking about with a triangle, we just working with nice positive numbers that measure the different sides of three sides of the triangle. But now we can work in some x values that are negative, y values are negative, and then also x and y values that are 0. Because if we're just talking about it as a triangle, it's kind of hard to picture it, but this will apply to any other point along that circle. So it doesn't necessarily have to draw in the right triangle each time, because it can work no matter what x and y value we're working with. So that's where I'm going to talk about these extra little things that I have next to it. So here it says that x can't equal 0, and the reason why that is if you think about we are writing a ratio, which means we're dividing. We can't divide by 0. So if x happened to be 0, we were trying to write out tangent if y was 3. So it would be 3 over 0, or 3 divided by 0, which we can't do. So the new thing that's introduced is if we do have 0 as our x value, which we don't have it super much, then what we say is that the tangent value is undefined. Okay. So whenever that happens, and like I said, we don't see that a whole lot, but again, if you ever have that happen where x was 0, tangent would be undefined, also secant would be undefined. So anytime you see this little this thing next to it, that's just an in case that happens. So if y was 0, then cosecant would be undefined. If also cotangent would be undefined. So again, it just happens that there's a couple of values that if we have a certain x and y value, we just can't do because we are still dividing. Now the radius of our circle will never be 0, so you don't have to worry about that with sine and cosine. But these other four, since it's using x and y on the bottom, we have the potential of having x and y as 0, then we have something that's undefined. And like I said, you don't have to necessarily worry about that too much, except when you're writing out ratios. So if you ever do have a ratio where you have to put 0 on the bottom of that ratio, then we would say that that value is undefined. So hopefully this feels familiar, because it's a lot of stuff that we worked with our right triangles. We're now just applying it here. So if you look at the direction, we bring this back this word, find exact values of the 6 different trig functions. So we're going to write out the ratios for sine, cosine, tangent, secant, cosecant, and cotangent. Only now, instead of being given a triangle as our information, we're going to just start with an x, y ordered pair, and then we'll use that to help us find the radius of a circle. If we imagine plotting that point and then drawing a circle around it, and then writing the ratios using x, y, and r, which again we can still think of it in terms of SOHCAHTOA. So you can keep that up there. But again, the biggest difference is that instead of having a triangle where we know the opposite, adjacent, and hypotenuse sides, we know the x value, the y value, and the radius. And so the x value is the adjacent side, the y value is the opposite side, and the hypotenuse is the radius of that circle. So here's our original x and y coordinate pair. So we have x and y. So I am going to try to sketch it a little bit. So imagine if we plotted this point. So we've done that way in the past. It's been a little bit, but -4, 3 would be something like that. And so then imagine drawing a circle based off of that point. So we're drawing that circle. I'm not going to draw a circle because I can't draw a perfect circle, so I'm just going to leave that alone. And so then imagine there's this circle that's going around here. So then what we do is there's going to be a radius of that circle, which is just this distance from the middle out to that point. So that's going to be our r. And then if we got down, here's our right triangle with r, y, and x. Okay? So you don't have to draw the picture every single time, but again, that's where the right triangle comes from. So now, like I said, the adjacent side is x value, which is our -4. The opposite of that would be y value, which is the 3. And the radius, we don't know, but we can find that. And that's the first thing we're going to find. So you're going to use this reimagined version of the Pythagorean theorem to help us find the radius of that circle if I were to draw a circle around and hit that point. Okay? So I have -4 squared plus 3 squared equals r squared. So a negative squared, whenever you square a negative, it becomes a positive. So you have 16 plus 9 equals r squared. So then 16 plus 9 is 25. That equals r squared. And we get rid of the square by using the square roots. So then here's where I'm just going to talk real quick about this word again. So remember, you have exact values, not have a perfect square root, we leave it as a square root. But I was nice to see on this first example, we have the square root of 25, which the square root of 25 does work out nicely. So our R value is 5. So now we know our three values that we're going to use. X is -4, Y is 3, and our R value is 5. So we write out our ratios. So sine is typically opposite over hypotenuse, but opposite is now defined as the Y value, and the hypotenuse is now the radius of the circle. So we're going to say Y over R, so 3 over 5. Cosine is now defined, is considered being defined as adjacent over hypotenuse. Adjacent is now the x value of this little triangle, so the x value over the radius of that circle, so it's x over R, so it's -4 over 5. So there's cosine. Tangent is usually opposite over adjacent, but again, opposite is y, adjacent is x, so it's going to be 3 over -4. Then we have cosecant, which is the reciprocal of sine. So sine was y over r, so cosecant is going to be r over y, so 5 over 3. Then we have secant, which is the reciprocal of cosine. Cosine was x over r, so secant is r over x, so 5 over -4. It's the reciprocal of cosine. And then tangent's reciprocal is cotangent, which tangent is y over x, so cotangent is x over y, so 3 over -4. And we're just writing exact ratios, and so that's once we have our x, y, and r, we can write out all 6 ratios using those values. Alright, so the biggest difference now is we'll have some that are negative. If I ever do give you as x and y is 0, if you ever have to put that on the bottom, that value would be undefined. But like I said, in this one, we move all 3 values pretty nicely, and so we were able to find all 6 ratios pretty quick. Okay, let's do another example. So you're finding all exact 6 values of our trig ratios. So we're given an x and a y. So the first thing we need to do is use our reimagined version of the Pythagorean theorem. So we can change x, y, and use that to find the radius of the circle. So we have 1 squared plus -2 squared equals r squared. So 1 squared is 1, -2 squared is 4. So then we add those together and we get 5. So we get r squared is equal to 5. And then again, we have to get rid of the square by using the square root. And then does 5 have a perfect square root? It does not. Okay? So again, we're leaving them as exact values. So since 5 doesn't have a perfect square root, we're going to leave it as a square root of 5 because that's more exact than rounding it. So now we're going to write our ratios. The sine is, like I said, typically is opposite over hypotenuse, but opposite is y, hypotenuse is r. So we're going to do -2 over the square root of 5. Which, if you remember from before, we like square roots on the bottom of our fractions. We sure do. So we have to fix that. We'll have to rationalize that denominator. Just multiply it by itself. So we take it times the square root of 5. So on the top, we're going to have -2 square root of 5. And then on the bottom, when we take square root of 5 times the square root of 5, we're just going to get 5. The square root of 5 times the square root of 5 is square root of 25, which is 5. So that's why we picked that specific thing to get rid of that denominator. So there's sine. Cosine is typically adjacent over hypotenuse, which adjacent is x, hypotenuse is r. So we have 1 over the square root of 5, which again, we have the square root of 5 on the denominator, which we don't like. So again, we multiply that by the square root of 5. Get rid of that square root off the bottom, so we have the square root of 5 over 5 for cosine. Now, like I said, typically when we're doing that, we got our 2. There's usually 2 that we have to rationalize that denominator, fix that denominator. So we've done that, so all the rest of them should be fine from here on out. So the tangent is usually opposite over adjacent, but opposite is y, adjacent is x, so we have -2 over 1. Now we could simplify that and just write that as -2 if you would like. So then we got cosecant. Cosecant is the reciprocal of sine. So sine was y over r, so cosecant is r over y. So it's the square root of 5 over -2. We'll just leave that. Secant is the opposite of cosine. So cosine was x over r, so So secant is r over x is the square root of 5 over 1, which again, you can just make the square root of 5 if you like. And then cotangent, that is the reciprocal of tangent. So tangent was y over x, so cotangent is x over y. So 1 over negative 2. So there is our 6 trig ratio. So now we're going to virtually do the same thing, only I can give you the information a little bit different. Most of the time I'm just going to give you an ordered pair, an x and y, use that to find your r, then you can write the rest of your ratios. Every once in a while, just like before, I didn't always give you a triangle. We could actually start with one of the values and use that to find all the other ones. Again, the exact trig ratios. So that's what we're going to do here. So I can start off by giving you a sign, which we're going to use our new labels. So sign is y over r if we use our values from our circle. So the top number is the y, which is like the opposite side. The bottom number is your r, which is like your hypotenuse. So if we're given y and r, what we're missing is x. So then again, we can use our reimagined version of the Pythagorean theorem using x, y, and r to help us find the x. So we'll leave x squared, and it'll be plus 5 squared minus or equals 7 squared. So we can solve that out. So 5 squared is 25. 7 squared is 49. We're going to subtract the 25 over here. Then x squared is equal to 24. And then again, to get rid of the square, we have to use the square root, which is 24 of an x square root. It does not. So we'll have to leave it as the square root. So now I have my x, my y, and r, and I can write the rest of my ratios. So I'm not going to write sine because I already have that, so I'm going to start with cosine. Cosine is x over r, so x is that square root of 24 that I just found, over r, which is 7. Tangent is y over x, so y is 5, and we have the square root of 24 that I found for x. So again, we don't want to leave that square root on the bottom, so we're going to multiply by the square root of 24. So 5 square root of 24 over 24. So then we have cosecant. Cosecant is the reciprocal of sine, so sine is y over r. Cosecant is r over y, so it's 7 over 5. Then we have secant, which is the reciprocal of cosine. Cosine was x over r, so secant is r over x. So again, we have 7 over the square root of 24. So there's our second one where I have the square root on the bottom, which we're going to fix. So we have 7 square root of 24 over 24. And then finally we have cotangent, which is the reciprocal of tangent. So tangent was x over y, so cotangent is x over y. Sorry, tangent was y over x, so cotangent is x over y. And there's our ratios. So we're going to do one more real quick. Sometimes we'll have negative values. So if something's negative, I just put it with the top. So we're going to keep the negative just with the top one. Again, they both can't be negative because if they're both negative, it would change to positive. So that we're going to give that negative to the top part of our ratio, especially with the cosine, because our radius will never be negative. So what's going to be negative is either x or y. And so since we have that negative, cosine is x over r. So our radius won't be negative, but our x will. So we give it to the top number. So then what we don't have is y. So we're going to use that x squared plus y squared equals r squared. So let's find the y. So I have negative 2 squared plus y squared equals 3 squared. So negative 2 squared is 4 plus y squared equals 9. So subtract 4 over here. So we get y squared is equal to 5. Take that square root. So y is going to equal the square root of 5. Because again, we want to leave it as an exact value. So now we're going to use -2, 3, and the square root of 5. So you need sine. So sine is y over r. So y is the square root of 5. R is 3. So let's have the square root of 5 over 3. I'm not going to write cosine because cosine is already there. So I'm going to go write the tangent. So tangent is y over x. So it's the square root of 5 over that -2. Cosecant is the reciprocal of sine. So sine was y over r. So cosecant is r over y. So we have to fix that square root of 5. So I have 3 square root of 5 over 5. Secant is the reciprocal of tangent, or not tangent, cosine. I would write it tangent when I said that. Sorry. So secant is the reciprocal of cosine. So cosine was x over r, so secant is r over x, so 3 over -2. And then we have cotangent finally. Cotangent is the reciprocal of tangent. Tangent was y over x, so cotangent is x over y. Again, that's our other square root of 5 on the bottom, so we have to fix that. So -2 square root of 5 over 5. Okay, so like I said, hopefully it seemed familiar because it's similar to when we did it with triangles, similar to when we did it with one value. Only now we're using it as in our x, y, and r circumstance, where we know a point on a circle, which we can make into a radius of that circle, an x value, and a y value, and then write our ratios based off of x, y, and r instead of opposite, adjacent, and hypotenuse. I'll post this as well as a PDF version of my notes. Hopefully it all made sense. Let me know if you have any questions. And